So in the last lecture, we discussed, sorry, what is pen? Zeeman effect. And Zeeman effect is actually the change in the energy levels or the shift in the energy levels because of the presence of magnetic field. That is when we place the atom in an external magnetic field. Then we discussed normal Zeeman effect, in which spin was ignored, spin s is equal to 0. And we also saw that the spherical symmetry is broken and the energy levels are shifted with an equal spacing of b mu b delta, and these are equally spaced. So that is one of the important property of normal Zeeman effect. They are equally spaced. Now, the another part of this effect, that is Zeeman effect, is when we consider spin of an spin angular momentum or spin magnetic moment of an atom, that is spin of an electron. And we assume that we have an atom which contains a finite spin magnetic moment s, total spin s, and then we also consider that there is an orbital angular momentum L. If you see, then we place this atom in the external magnetic field B, which is directed along z axis Bz. Then we have the Hamiltonian for the interaction between the total magnetic moment of an atom and the external magnetic field, that is Hz, which will be equal to minus mu L dot Bz, or simply B, let me write it B, and there will be added term of mu S dot B. This is the interaction energy or the perturbation energy or the energy stored in a dipole when it is placed in an external magnetic field. This is what it means. This is a general expression, a 12th
Sir,
class.
negative sign here.
Negative sign is always, you already know that this what it is, that this mu magnetic dipole moment and the L, that's in the opposite direction. Okay, and also when you place the electron in an any dipole in external magnetic field, it tries to align that dipole moment in its own direction. Okay, in any case, both the dipole moments mu s and mu l, they are actually kept as they are opposite to the direction of magnetic moment. Okay, so they have direction opposite to that magnetic field. Those moments have opposite directions to the field. That is why it comes negative there. And we also know that this mu is minus e by 2 mc, so I can write it as it becomes plus here into L dot B minus plus, sorry, this will be now plus here because of that S dot B. So if you take the interaction, so these are the values of mu L and mu S, this, and this is the B, interaction between B. Now since B is along Z direction, so we have a component of the L which will be along Z direction, and we will have a component of S which will be along Z direction. That is space quantization. And then we can write H equal to H naught plus, there is also HF S plus HZ. What is this? This is fine structure term because there is spin angular momentum, there's an orbital angular momentum, there's an interaction between the two that will give rise to the fine structure. Okay, then there's a Zeeman interaction because of the external field. So these are the total interactions for an atom which is placed in an external magnetic field. Now we have two cases from here. Two special cases. Number one is that is called as strong field Zeeman effect. And this is also called as Back effect. And we have weak field Zeeman effect. This is normally called as Zeeman effect actually. This is more steadier. And in strong field Zeeman effect, what happens is that
spin is not zero.
Spin is not zero in both these cases. In strong field, in weak field. So it is actually strong field anomalous Zeeman effect here. This is weak field anomalous Zeeman effect. So in both the cases we consider the spin, but there is a competition between the external field and the internal interaction, internal fields. That means external perturbation and the internal perturbation. So that is the competition between them. So in strong field case, so it is strong with respect to what, or it is weak with respect to what? Let us see that. Remember that both HFS and H0, HZ, sorry, they are small as compared to H0 individually. They are small as compared to H0. So it is treated as a perturbation, these both. Now we also know that H spin orbit or H fine structure, what we call, because fine structure, the contribution to the fine structure here is spin orbit. We are not considering the relativistic correction into this. So the main contributors to the fine structure in this case is spin orbit interaction, because we are taking the combination of spinor orbital angular moments now. So the spin orbital angular momentum becomes the spin orbit interaction becomes the main contributor to the fine structure. So this spin orbit and Zeeman term, these two. If you write, we can write this HSO. This is an interaction between. So let us it be L dot S because it is spin orbit interaction. We have already done this. And if it is interaction is determined by some parameter W, this is some constant it will determine its interaction. Okay, there's an interaction energy of the spin orbit interaction. Let it be defined by some parameter W. Okay, and this W is some, it depends, it is because of the interaction between the L and the S. Okay, so it is WL dot S. And we also know that Z can be written as it is B mu B. यहाँ मैं लिख सकता हूँ, it is LZ plus 2 SZ. Can I write? Here, this equation. I can write it here. Okay. So E by 2m EC is mu B.
Yes, sir.
And there is a H cut in the division in the denominator. Because mu B has an H cut in the numerator. Okay. SL plus this. So if you take the ratio HZ divided by HSO, you can see that it is approximately equal to, approximately, not rough, not exactly equal to, the parameter which is varying, that is B. Okay, the interaction is defined by W. There's a mu B here. So I have not taken these two, L dot S and L plus S. This is an approximate estimate. Now, if you see this, when B is much less than, what will happen? When B is much less than W by mu B,
Z by
what will happen to this equation?
सर ये भी लेस ही होगा फिर कम
Or
होगा
simply,
Z by
let us take it another way. Let's take it another way. So Hz by SO, I can write it as, it is approximately equal to B mu. Mu B is a constant, let us forget mu B. I can write B is much less than W. What will happen? It gives us that Hz is less
Z by
than,
HSO
is it okay?
so
Similarly, when B is much greater than W, is, can you understand this? These two
सर
cases?
ये दोनों टाइम्स पे होगा HSO स्मॉल देन HZ.
Yeah, greater than, this is not small.
रिवर्स
रिवर्स यस सर.
रिवर्स में होगा ना ज्यादा
Okay, now, so this is the important point to understand when we treat it as a strong field case or when we treat it as a weak field case. Now remember, we have an internal interactions. Now if, and we have an external interactions. Internal means this SO, this means Z. Okay, when the external, when this external field is strong, that means when the external interactions, that means this is strong, this is much greater than this, that means Hz is much greater than HSO in this case. So this becomes the strong field case. This strong field case. And when HSO becomes greater than Hz, this becomes weak because internal perturbations at that time will dominate. It does not mean that we are ignoring the external perturbations because we are then leaving the Zeeman effect. So at that time, we have to consider both the external as well as the internal, because once we lower the strength of the external field, the contributions will be equally important, both from the Zeeman and both from the spin orbit interactions. So in the strong field case, it is such that it is strong such that the internal interactions, that is internal spin orbit interaction, becomes less dominant. It does not have much effect as compared to the external field. So at that time, we can ignore the spin orbit interactions. This is the point to understand, that when we say that it is a weak field case or when we say that it is a strong field case. So if anyone has confusion here, please let me know. When B is strong, arrow upwards means it is more, and this external field, then and let me write it as external and B internal. So B external is strong and B internal decreases. That it's not decreasing, actually it is lower than the external field. The strength of the external field is much greater
Front
than the internal strength. Internal means that spin orbit interaction.
internal.
Okay,
Yes, sir.
spin orbit. So when spin orbit interaction is very small as compared to this external, we can
External field.
yeah, we can ignore this internal interactions. So the interactions are ignored at that time. So that becomes the strong field case, because external field is much greater than the internal. And in opposite of that will lead to the weak field case. And weak field means that field is weak. It is not zero, but it is weak. External field. Because once we ignore the external
And
field, we are not taking Zeeman effect there. Because Zeeman effect is only studied when we have external magnetic field. So at that time, when we have a weak field case, we have to consider both the external perturbation and the internal perturbations. But in the strong field case, we have only take the external perturbation, because the external field is much greater than the internal. Now let us take the first case. Strong field case. So strong field case means that external field interactions are much greater than by this internal spin orbit interactions. That means the term EB LZ plus twice SZ will be much greater than the fine structure term. Okay, and we can write then H will be equal to H0 plus Hz, which is H0 plus now solving this like we did in yesterday's class, in the previous class. How we take them? Energy eigenvalues, as H will commute with H naught, because H naught commutes with LZ and SZ. When there's this commutation relations, then we have a common eigenstate, common set of states, which is represented by N, L, ML, and MS. ML, MS from these two, and it is equal to, I can write H0 plus EB is whole, and there is N, L, ML, MS in this case. So it gives us E. It is En 0, the ground state. So EB H cut divided by 2MC. This will be ML plus. When we operate, it is like this. You have NL, ML, MS, LZ, NL, ML actually, and this will not be here. And you have NL, MS, SZ, twice SZ actually, NL, MS. Okay, So these two cases. That is how it comes ml plus 2ms.
Yes, sir.
Now, just remind the previous class. Here is the perturbation energy. Perturbation term are the shift. So the delta is actually equal to EB h squared by 2MEC, and there is an ml plus twice ms. This is the Zeeman shift in case of a strong field case, when we ignore the spin orbit interactions, because the internal interaction, those are the internal ones, and those internal ones become less dominant. They have a very weak effect, very weak effect as compared to the external field. So what it gives us? It gives us that the energy level En0 or the shifted by an amount equal to, it is B actually, and mu B into ml plus 2ms. Here this term is mu B except without B, and this B mu B into ml plus 2ms. We know that mu B is equal to EH squared by 2mc, and this effect is known as Pastenbach effect or Pastenbach shift. The shift is known as Pastenbach shift. So when B is 0, if you put B equal to 0 here, the degeneracy is, the shift is 0. And in the case where the Hamiltonian contains several perturbations, then we have to treat them individually. First we will see that what is the most dominant, then what is the next most dominant, then to see the order of those perturbations we will treat the problem. That is how the problem is treated actually. So remember that it is important here that when B is equal to 0, the degeneracy is given by Gn, number of terms, that is 2 summation of L equal to 0 to n minus 1, that we know. L goes from 0 to n minus 1, it is 2L plus 1, we already done this. That is actually 2n square. But when B is not equal to 0, the states degeneracy is lifted, but the states with same ml plus 2ms are still degenerate. These are when this is not equal to 0. There is a degeneracy is lifted, but the states with same ml plus ms 2ms, they are still degenerate.
Sir, example.
Yes, we are doing the example.
Say.
Let us see. Remove this line. Please remove this line. Somebody has drawn this. I think Insha. Using the whiteboard of Zoom, please remove that. Huh? Okay. Now let us take an example of n equal to 1 level. Let it be n equal to 1. We have n equal to 1, remember that. Then b is equal to 0 here. When n is equal to 1, we have n, l, ml, and ms. So what is for this case? What is the n equal to 1? What is it?
L equal to 0. L equal to 0.
L equal to 0. So it is 1, 0. ml is also equal to 0 plus minus
0 plus minus
1 by 2.
By 2.
Okay. So this is the level.
Yes, sir.
When this is the level, and we have the degeneracy here, that is GL equal to 2 electrons. when n is equal to 1. We already know that for S state. And when we keep it in strong magnetic field, it is N,
Anamolous is lifted.
L, ML, MS.
MS.
It is 1,
And
0, 0, minus 1 by 2.
0 minus 1 by 2.
This is 1, 0,
0
0,
0
plus 1 by 2.
0 plus 1 by 2.
That is how the levels are degenerate. And the energy here will be E10 minus B mu B, because ML and MS are now, can put up the values there. So minus B mu B, and this will be E10 plus B mu B. This is actually B mu B ML plus 2 MS. So ML is 0. So it is B mu B ML is 0 plus 2 into 1 by 2. 2 and 2 cancel. So it is 1. So it is
1 by 2. 1.
minus
Yes,
1
sir.
by 2 for this case, plus 1 by 2 for upper level.
Yes, sir.
Okay, let us go down. So if for n equal to 2, so forget about this line, red line. Let us suppose n equal to 2. So when n equal to 2, we have 8 states actually. G2 is
Yes,
equal
sir.
to 8. This is G1, not GL. Sorry,
8.
this is G1. So G2 is 8. So we have the states 2, 0, 0. We have plus minus 1 by 2 here.
Plus minus 1 by 2. Yes.
We have 2, 1, 0. Plus
1
minus 1
0
by 2
plus minus 1
by 2. Okay, we have 2, 1, plus minus 1,
plus minus 1
plus minus 1
plus
by 2.
minus
Okay, so these are the states here.
2. Yes.
Now I will shift towards the right. This is n equal to 2. So L equal to 2. Sorry, n equal
2
to 2, L
1
equal
0
to
1
0 and 1.
0 1
So we have how many states here? 5 states. Now let us see how it is.
5, sir. Plus 1.
Let us take this first central one. So it is 2, 1, 1, minus 1 by 2, and 2, 1, minus 1,
1
1 by 2.
1 by 2.
Because this is E20 actually. So you have to see the combinations for which this term ML plus 2 MS is equal to 0. That corresponds to this level.
Yes, sir. Mm.
Now this second level is E20, sorry, last level, minus 2B mu B. Because 2 is already there. And this is E20 minus B mu B. This is E20 plus B mu B. This is
B
E20 plus
0
2
plus 2.
and this combination corresponds to 2, 1, minus 1, minus 1 by 2, and this corresponds to 1, 1 plus 1 by 2.
1 plus 1 by 2.
Similarly, this combination is from 2, 0,
2
0,
0
1 by 2
0
and
plus
2, 1, 0, 1.
0 1.
Because same ml plus 2ms is degenerate now. They are in the same level, having equal ml plus 2ms. That will be given by this. We can calculate that from this value. Then this is 200 minus 1 by 2, and it is 210 minus 1 by 2. So this is the case for a hydrogen atom splitting of the energy levels. So n equal to 1 and n equal to 2, these are splitted when the hydrogen atom is placed in strong external field. This is the strong B field, so B is not equal to 0 in this case. This is the strong field case. There any confusion here to anybody?
सर अगर हमें इनमें भी डिजेनरेसी लिफ्ट करनी होगी तब?
We will see that in the weak field case.
Okay,
because
sir.
that at that time we will take L and ML and MS both. Here we are not taking those actually, because we are ignoring the internal interactions.